Hi, I'm Debbie Nelson with Nixene Publishing, coming to you from the United States. And we are continuing our series about graphene with Adrian Nixon, who is editor-in-chief of the Nixene Journal. And he's coming to us from Yorkshire, England, right, Adrian?
Very sunny Yorkshire today, yes.
So today we're talking about something that I don't think we've talked about before. You know, the Nixene Journal for our viewers is features the world of graphene and other 2D materials. And I don't think we've talked about other 2D materials, have we?
We haven't. We've been so carried away with all the graphene stuff that we haven't even talked about this hinterland of 2D materials. We
Yes.
better explain to the viewers what these are, I suppose.
Yeah, that sounds good because I remember Andre Geim telling you when you interviewed him that there's so many that it could keep us busy for keep researchers busy for their whole lives.
Yeah,
So
and him too. Yeah.
yeah, so
Um,
what's going
right.
on?
Just a quick recap. One of these molecular models again. You know, I've got a weak spot for molecular models. This is, as viewers, regular viewers will know, is this graphite. So we've got one layer of carbons, all hexagons. It's all the same material. It's all carbon. And the hexagon layers, each layer, one layer is graphene. They stack up into graphite. This is, I suppose, strictly speaking, three-layer graphene. The reason I'm showing you this is because 2D materials are effectively the flat sheets in these structures, but this is an example of something called a van der Waals homostructure, and 2D materials are sometimes called a van der Waals heterostructure. And what it means is there's more than just one type of flat structure. This is one of the reasons that, well, it's Andre Geim's paper after he won the Nobel Prize, which is probably more important, is that he basically discovered this whole world of other 2D materials. So you can get flat things that are made up of compounds which are other than carbon, and they can exist in isolation and get paired up with graphene. So this is called a homostructure. A heterostructure would have different types of chemical compounds in there. Does that make sense so far?
Okay, so it would be stacking something else in between the layers?
Exactly, yes, yeah. And the van der Waals bit, you see these purple links here? These
Yes.
are called van der Waals bonds. We won't go into that now. I think should we cover that separately in another video, Debbie? Because
Sure.
I'd like to do that justice. But basically, they're weak bonds which hold the layers together, and that's enough for us for the moment, for our purposes. Otherwise, we'll end up with a very long video. So
Great.
I need to share my screen again. And there is one thing that these other materials, van der Waals heterostructures or 2D materials, seems a bit of a mouthful. So some of the people in Manchester University, particularly James Baker, refer to them as graphenes. I think Andre Geim originally came up with the term, which is quite a nice way of encapsulating the whole field, although I think the academics are retreating a little bit from graphenes and they're going more down towards van der Waals heterostructures these days, just because they like to be precise. So all these terms, graphenes, van der Waals heterostructures, 2D materials, they all mean the same thing pretty much. And there are thousands of these 2D materials. They exist in all sorts of forms, and they have all these weird names here. Molybdenum disulfide, boron nitride, molybdenum diselenide, similar but different, tungsten disulfide. What they look like, this is a side view of one, they don't look as simple as graphene, so they're not just one atom thick, they're several layers thick. But when you look at them from the top, they have this honeycomb structure. The important thing is, as we've said, you can layer them up like a club sandwich. And by layering them up differently, you can create entirely new materials which have never existed before, which could have amazing properties. So you've got the ability to create designer materials. And this is what Andre Geim meant, Debbie, when you were talking earlier, saying that there's a whole field of research which is going to keep people occupied for the next generation.
And that's because they realized that they could separate the single atomic layer, right?
Exactly, yes. Do you remember we talked about the National Graphene Institute in one of our videos, Debbie, the NGI in Manchester?
Yes.
They have lots of scientists down there who specialize in peeling apart these one atom thin layers, and then they can put them back together again and sandwich them up. And they got very good at this, so they can actually by hand manufacture these things and just see what the properties are. And there's a lot of guesswork in this, just trying stuff and see what works, and then some inspired intuition as well on the part of the researchers. One family of these things is something called a transition metal dichalcogenide. Yeah, I know, yeah. It's a bit of a complicated term, isn't it? But basically all it means, these are transition metals in the periodic table. Do you remember the periodic table from school?
Absolutely.
That's good. This block here in the middle, they're the transition metals, and some of these, particularly these top two rows, from there, they're the metals that are currently being evaluated. And then this column here, from oxygen down to polonium, that's called the chalcogens. But for our purposes, we're only talking about sulfur, selenium, and tellurium. And so we can get 2 atoms of sulfur, selenium, or tellurium, and then 1 atom here of the transition metal, hence transition metal dichalcogenide. This is what they can look like. So this is a generic structure where the black atom is a transition metal, and then the yellow one is one of the chalcogens, so a sulfur, selenium, or tellurium. You can see that they form these what look like fairly complicated structures, but really all you need to know is that they're flat, and then when you look at them from the top, they're sort of hexagon-like. So you can see there's a similarity there with graphene. Does that make sense, Debbie?
Well, it really does. And when you used your molecular model and you held it up, if you could imagine that one layer was one of those and the next layer was the different layer.
Exactly right. Yes. And those same van der Waals bonds hold all the layers together. They help them stack and keep the integrity of the structure, or the club sandwich, if you like, intact. If we have a look and see what you can do with them, we just pulled out one example from the journal from last year. This is interesting. This is so what we're looking at here is silicon dioxide, silica substrate. So just think of that as a piece of glass. Then you can just see the grey line here. This is graphene. So the graphene sort of goes under these chromium and gold connectors. They're basically just an electrical contact. And the graphene conducts electricity into this stack. And the blue layers are hexagonal boron nitride. We'll talk about that in another video. Then we've got a layer of tungsten diselenide. Then we've got a layer of boron nitride again. Then we've got molybdenum disulfide, another one of these transition metal dichalcogens. And then we've got a few layers of boron nitride again before we've got it capped off with graphene. So you can see that's what the club sandwich is like. And what it's actually doing is, when you put an electrical current through from the top of the stack to the bottom of the stack, it emits light. You can control the wavelength by controlling the applied voltage. So you can change the color of the light that gets emitted too.
Oh, that is cool. And do you think that they were looking for light, or do you think they just found it by stacking?
That's a really good question. The honest answer is, I don't know. My guess is that it was probably somebody had an inspired guess, but they didn't really know, because trying to predict what happens in these stacks is very difficult. I think at the moment, what a lot of people are doing is just trying stuff and see what works, modifying it to see if they can make it any better. But this looks like it could be a very efficient low voltage LED that you can change the color of just by changing the voltage. So that's one of the things you could do with one of these transition metal dichalcogenides. So I'll stop sharing there and come back again.
Yeah, that is really handy if you can just change the voltage to change the color like that.
Yeah.
That seems handy.
Yeah. So you can do practical things with these heterostructures, van der Waals heterostructures, these club sandwiches. And we're going to spend the next generation, it'll keep us going, Debbie, reporting on all the work that people are doing with all these stacks, and we'll find out what amazing things people are able to do and then scale them up into production too.
Oh, absolutely. I'm looking forward to finding out more about what people stack and what comes out of it.
Yeah, and because we go right into the research, the early research, but we also go right through to the commercialization as well, we can follow these things through from inspiration right through to industry.
That's going to be exciting, and to see how quickly they can do it. Adrian, thank you so much. This has been great, and we'll get back together again and do another video, and we'll see you soon. And for our viewers, please leave us comments or questions if you have any for us, and we'll be happy to get back to you. Thanks so much for watching.